All right, here we go. I'm on my fifth video to help you guys get ready for the fall semester exam. And this one is specifically for the Calculus BC students who just completed a unit on rate functions and the definite integral. Here we go. For the time interval 0 less than or equal to t less than or equal to 20, the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w is measured in degrees Fahrenheit and t is measured in minutes. Now, that all might be really important. Maybe it is, maybe it isn't. I don't know yet. At time t equals 0, the temperature of the water is 55 degrees. The water is then heated for 30 minutes, beginning at time t equals 0. Values of w of t at selected values of t for the first 20 minutes are given in this table above. Okay? Part A. Use the data in the table to evaluate the definite integral of w prime of t with respect to t from 0 to 20. Then, using correct units, interpret the meaning of that answer. Well, how are we going to evaluate the integral from 0 to 20 of w prime of t dt? Oh, and if I forgot to mention it, this is a calculator active question. Now, since it's calculator active, you might think, well, let me just plug this into my calculator. The problem, though, is we don't actually have a function. We don't have an equation that we can plug in for w prime of t, so the calculator is not going to be that helpful right now. What is going to be helpful, and this may catch you by surprise, is the fundamental theorem of calculus. The fundamental theorem of calculus says f of b is equal to f of a plus the integral from a to b of f prime of x dx. I like to explain this as the value of the function at the end value is equal to the value of the function at the beginning plus the integral from a to b of f prime of x dx. This represents the total change in the function. Well, if this is the fundamental theorem of calculus, by subtracting f of a from both sides, I can also say that the integral from a to b of f prime of x dx is equal to f of b minus f of a. Both of these count as the fundamental theorem of calculus. So if I'm integrating the derivative of a function, the value is going to be the value of the function at the upper limit minus the value of the function at the lower limit. In this particular example, the definite integral from 0 to 20 of w prime of t is going to be equal to w of 20 minus w of 0. I'm going to go to my data table. W of 20 is given to be 71. W of 0 is 55. That difference is 16. Now, 71 is being measured in degrees Fahrenheit. 55 is being measured in degrees Fahrenheit. So this value of 16 must also be measured in degrees Fahrenheit. What does this answer mean? Well, W represents the temperature of the water. W prime, the derivative, is telling me at what rate is the temperature of the water changing. The definite integral represents the total change in temperature. So I'd want to say it this way. From t equals 0 to t equals 20 minutes, what happened to the temperature? The temperature of the water increased. Don't use change if you can be more specific and say increased or decreased. Increased by 16 degrees Fahrenheit. We awarded 1 point for coming up with the numerical value, and then we awarded a second point for 2 points for being able to explain the meaning of your answer in the context of the situation. That was part A. In part B, for the time interval 0 less than or equal to t less than or equal to 20, the average temperature of the water in the tub is 1 over 20, the integral from 0 to 20, w of t dt. Using a left Riemann sum, that's important to pay attention to, with 4 subintervals indicated by the data in the table, to approximate the value of this integral. Does this approximation overestimate or underestimate the average temperature of the water for these first 20 minutes? Well, let's see. They said a left endpoint method. I'm going from t equals 0 to t equals 20. Now, before you get too excited and you say, oh, okay, if I'm going to go from 0 to 20 and I'm going to use 4 rectangles of equal width, then the width of each rectangle would have to be 20 divided by 4 is 5. The reason I need you to slow down is at no point in this problem does it say that the rectangles have the same width. In fact, they specifically say use a left Riemann sum with the 4 subintervals indicated by the data up here. Well, let's bring these together and look at the data. I know the value of the temperature at time 0, at time t equals 4, at time t equals 9, at time t equals 15, and at time t equals 20. These are my 1, 2, 3, 4 intervals that I'm interested in. So I'm going to get 1 over 20 times the definite integral using the left endpoint method. What I need to do is take the base, the length of that interval, which is 4, times the height of the function, which is w of 0. W is the function. I want to make sure I use the proper function name. That's the first one. The second rectangle has a width of 5, and then I find the temperature of the water at time 4. The next subinterval has a width of 6, and then I find the temperature at time 9, check. The last one has a width of 5, and then I need the temperature at 15. So that's going to be 4 times 55.0 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9. Now remember, this is calculator active, so feel free, take a moment, plug that into your calculator. You also could, if you wanted to, just stop here because everything is a number, so that gets you the full credit there. If you go and plug this into your calculator, you should get 60.790 degrees Fahrenheit. Not bad. Now we're going to go a little bit further. Because what did they ask for in the question? They said find that value and then determine does this approximation overestimate or underestimate the average temperature. Well, is there anything that we know about W? We were told in the beginning that W is strictly increasing. So if I were to consider a graph, and the graph is not going to be your justification, I know I've got all of these points and the function is strictly increasing. So my graph will look something like that. We're going from 0 to 20. So here's t equals 0, here's t equals 20, and we're using the left endpoint method. So for each subinterval, use the point on the left, go up to the curve, over and down. Point on the left, up to the curve, over and down. Point on the left, up to the curve, over and down. I can see that this is going to have to be an underestimate because my rectangles are not capturing this area. Your write-up, though, is you're going to have to say this is an underestimate, not because of the graph, but because of what we know. I'm sorry, not because of my sketch, but because of what we know about the function. What do we know? This is an underestimate because w of t is an increasing function. And we are using the left endpoint method. When we awarded points, we awarded 2 points for this initial setup expression. In fact, you could have earned the 2 points here, or you would have earned the 2 points here. These are the same. The difference is you cannot stop here because these are not all numbers yet. At the second line, you could stop and be done. And then you earn the 3rd point for your justification for a grand total of 3 points. Okay. Let me take a second. Move forward. I want to make sure that I know what I'm doing with part C. All right, in part C, now we're told for the time interval 20 less than or equal to t less than or equal to 30, the function w, hold on one second, let me fold this back. Okay. For the time interval 20 less than or equal to t less than or equal to 30, the function w that models the water temperature has a first derivative given by this expression here. Based on the model, what is the temperature of the water at time t equals 25? So I want to know temperature of the water at time t equals 25. I need w of 25. I've been given w prime, and this function is valid on the time interval 20 to 30. Well, I need to know the temperature of the water at some point in time. I know the rate at which the temperature is changing. What I need to know is an initial temperature. Now, a big mistake students are going to make is they're going to say w of 0 plus the integral from 0 to 25 of w prime of t dt. And you might be thinking, well, what's the mistake? The mistake is that w prime is only valid on the time interval 20 to 30. So we can't find the definite integral from 0 to 25 of this function. That function doesn't model our situation on the time interval. What we can do is we can say the temperature of the water at time 25 is equal to the temperature of the water at time 20, which we do know, we were given that in the table above, plus the integral from 20 to 25 of w prime of t dt. That is a valid statement. We know the temperature of the water at time 20 is equal to 71 degrees. So 71 plus the integral from 20 to 25 of w prime of t dt. All right, let's see if we can do this. This is a calculator active question. What I decided to do is I went into, I don't know if I'm still recording. Okay, good, I'm still recording. I've not used the graphing calculator and the recording software before. So I graphed the function. Now you can't do 0.4 times the square root of t. You're going to change all the t's to x's. 0.4 times the square root of x, cosine of 0.06x, on the time interval 20 to 30. That's my graph. Now let's go over to the computations, and I want to do 71 plus the integral is menu, calculus, numerical integral. I'm going to integrate from 20 to 25. The function name that I'm using is f1. Oh, what's going on there? Caps lock, sorry. f1 of x, and I'm integrating with respect to x. And that's going to give me 73.043 is my final answer. 73.043 degrees Fahrenheit. That's your final answer. The initial integral setup, the w of 25 equals w of 20 plus the integral from 20 to 25, was worth a point for a grand total of 2 points. Okay, I'm going to have to pause the recording so that I don't go over the 15-minute limit, and we come back to part D in just a bit.